Our next speaker is Professor Susan Burns. Susan Burns, a professor in the School of Civil and Environment Engineering at Georgia Tech. She is a ISEG Council member. Professor Burns' research focuses on the applications in geoenvironmental engineering, with particular emphasis on the productive reuse of waste materials, treatment of highway stormwater runoff using engineered material, erosion control of soils, and highway rights-of-way interfacial behavior of organic and inorganic coated soils, transport and behavior of microbubbles in saturated porous media, and hydraulic conductivity and consolidation of fine-grained soil using seismic piezo penetration testing. Today, our topic is fundamental behavior of waste material and implication for beneficial use of coal ash. Professor Susan Burns, please.
Thank you so much, Professor Du. It's really my pleasure to be here, and thanks to the committee for the invitation. So my work today I'm going to show is the collection of quite a few different students and research assistants here. So the first thing that I'd like to do is acknowledge their contribution, because these are the folks who are doing the heavy lifting. It was a great first presentation, and I'm happy to follow on with some of the work that we've been doing in sustainability and sustainable systems, in particular looking at ash deposits in the United States. So what you'll see for the work that we're thinking about is, in terms of sustainability, we know that we've got environmental, economic, and social conditions, and these are all going to come together ultimately with our goal to maintain and improve the quality of life indefinitely. So we know that we want to do that without degrading the resources in terms of natural, economic, and social resources that we have. So the triple bottom line model of development is how this is usually described. Typically, when we're looking at beneficial use of waste materials, we know that they must provide a functional benefit. They must substitute for virgin material. They have to meet relevant product specifications, and they have to have comparable or lower environmental releases than those from analogous products. So essentially, when we think about this, what we want to do is take a look at coal combustion products. We know that these are solid materials that result from the combustion of coal for generation of electricity, and they include a very large group of different products, very different properties as well. And so what you'll see here is that we produce a great deal of gypsum due to the desulfurization process in energy production. And we also have other materials which we refer to as bottom ash and boiler slag. Today, what I'd like to do is focus on fly ash. In the United States and in most parts of the world, we have a group of ash that's known as off-specification ash. And in these cases, these are ashes that maybe were produced by combustion of biomass, or ashes that have very large organic contents remaining, residual organics present, or fly ash that's been ponded as a disposal technique for years or sometimes even decades. So what we'll see here is we want to think about a few research questions. How do we increase sustainability through beneficial use? That's our first driving question that we deal with. Also, we want to think about how do we supply concrete demands into the future. In the southeastern United States, there are times of the year where there is not enough fly ash to meet concrete demand. And we're actually looking at importing fly ash and have imported fly ash in some cases. And then finally, how do we use these large deposits of high organic content and off-specification ash in construction materials? So again, these are things like the ponded fly ash that you see here in the left-hand side of the screen. Right, these are materials that have been put in place for quite a long time. And now in some cases, we're going to excavate them, move them, and redispose them as well. So let's think a little bit about what fly ash is to make sure that we're starting on the same page for everybody. So we know it's a fine-grained particulate material. Typically, you'll see here that it's captured by emissions control. So we have control over the collection process. It's an aluminosilicate material. So the chemistry has things in common with clay particles that we deal with more frequently. We also have two primary categories that I'll talk about today. One is class F fly ash, which is a pozzolan, and it's typically formed by the combustion of bituminous or anthracite coal. So the pozzolan we know is not cementitious, but if it's finely divided, we can get it to react with calcium hydroxide. We also have Class C fly ash, which is both apozolon and cementitious. And this ash forms from the combustion of lignite and subbituminous coal. So the characteristics when we look at ash are these cenospheres that you see here in the SEM images. These are very nice, relatively uniform, predictable sized particles, very easy to deal with. And when we add them to concrete, not only can they serve as a cement replacement, but they can also improve the workability. So there's some advantage to having fly ash, many advantages to having fly ash present in the concrete. The top image that you see there is a very low carbon fly ash. So it's very ideal for use in cement. When you look at the fly ash in the bottom picture, though, what you're gonna see here are residual organic carbon structures. So these are carbon particles that were not combusted, and that's due to a variety of different reasons, but they're present within the ash, and they are a problem for us because they react with air entraining agents, which are relatively expensive, and they take those up and they cause trouble in terms of the consistency of the product of the concrete. So we don't want to use typically high carbon ash in the concrete industry. Let's think a little bit about what biomass fly ash is, because it's a different animal than the other materials that we'll talk about today. So we know when we look at coal fly ash, we'll categorize that into Class F and Class C based on a variety of different properties, including the calcium oxide content. And then we have controls or restrictions on the loss on ignition as well. When we look at biomass fly ash, though, what we are doing here is we're combusting a variety of different wood products. So this can be wood, it can be grasses in some cases. In the United States, we combust urban wood waste as well. So things like pallets from shipping containers often go to biomass energy plants. In both cases, what we'll see is that the geotechnical properties can be very similar. So in general, this is a silty material. It can be low or high plasticity. Specific gravity will range from a little bit less than 2 up to as high as 3. On the low end, we have a high organic content. On the higher end, our iron oxides tend to increase. And generally what we'll see is that it has a saturated conductivity, as we would expect, as a function of particle size on the order of about 10 to the -5 centimeters per second. So when we think about ponded fly ash, it's a little bit different. What we do with fly ash that comes out of the plant historically, if we can't dispose of it in a dry landfill, we will sluice it into an ash impoundment. And so this is generally a river that has been dammed, and we transport the ash hydraulically and let it gravity settle behind the dam. What this means is that these ashes weather over time. So they start as a silty material, particle size does not change, but what we'll see in the work that we've done is that these are similar to unweathered Class F coal fly ashes. There is variation in the carbon content, so that means a measure of the loss on ignition or the total organic carbon, as well as the specific gravity. But what you can see here is that we've got loss on ignition for some of the ponded ashes that we've tested that have varied from as low as about 3% up to as high as 15%. So that's a pretty big range. And that is challenging for a concrete producer because we need consistency in the incoming product. So let's talk a little bit more about what this means for us in terms of how we're going to use these materials beneficially. We know around the world that our waste streams are becoming increasingly complex, particularly as we start to implement air emissions controls. This is going to come in and cause a waste stream that has more of the pollutants held within the solid phase as opposed to being discharged to the atmosphere. So what that's going to tell us is that the properties maybe are changing more quickly than we expect them to. Our disposal practices have changed, and those air regulations have become much more strict. So what we end up with are mixtures that have different physical and chemical properties, and we have some issues with quantity and supply. In the United States, you'll hear a lot of discussion about the role of coal in our energy picture. What you'll see here is that over the last couple of decades, with the increase in fracking and the relative decrease in the cost of natural gas, our percentage of natural gas or methane in the energy stream has increased substantially, while coal has decreased quite a lot. So coal at one point accounted for roughly 25% of our energy source. And now you'll see here that it's down to somewhere between 10 and 15%. So what is this going to tell us? What do we know about the fly ash characteristics that we're dealing with? So in particular, what I'm going to do here is show you a few different types of ash that we have dealt with, and then we'll talk about the different properties or the different abilities of those ashes. So here in the upper left-hand corner, what we see is a very high quality fly ash, very clean cenospheres, perfect ash for use in high quality concrete. When we look here on the right-hand side, what you'll see again is that residual organic structure. So these are total organic carbons of some form that for whatever reason have not been combusted. These cause us problems and generally are a little bit more tricky to deal with. What we'll see down at the bottom, though, is a couple of test runs that we've done with Southern Company here in the United States where we co-combusted coal and biomass. So essentially we have the coal stream into the power plant. It's very finely ground, and we combine that with a biomass stream as well. And you can see when you look at these pictures, there's a residual woody structure that remains, which is not combusted. In addition to that, on the right-hand side, what you'll see is an ash that was formed by combusting pure biomass. So in this case, you see none of the cenospheres that we saw here from the coal biomass co-fire. Again, we see the residual woody structure, so it's primarily unburned carbon that's remaining, as well as calcium and a variety of other elements that we have left over from the combustion process. Now let's look at an ash that's been sitting underwater in the southeastern United States, meaning it's pretty hot and humid throughout most of the year. And what you'll see is a different morphology than what we've seen in some of the previous SEM images. You can see here that we've got a change in the surface texture. So we've got residual weathering effects which have come in and dissolved some of the elemental or some of the molecular mineral phases that were here, and they've redeposited them on these particle surfaces. You can see some cementation effects here as well, and just essentially change or evolution in the morphology of these ashes. It makes sense, right? Because we know that when we have ash deposits, if we look at the groundwater, sample the groundwater around those ash deposits, we'll see characteristic plumes with dissolved constituents, things like boron and sulfate, chlorides. We know those all leach from the pond, and that leaching effect is going to leave ash particles here, which have a changed morphology, somewhat changed chemistry as well. In terms of geotechnical properties, when we look at the particle size distribution, our coal ashes and our co-fired ashes come here, and they'll classify in the USCS system as a silt. Most of the biomass plants that we have dealt with are actually not full-scale power plants. And what you'll see as a result of that is that we get a much larger grain size distribution. You can see these in green here are ashes that were produced by combustion of pure biomass. We have a much larger D50, and you can see here that our uniformity coefficient is larger as well. So why is this? What's going on here, and what is it telling us? What we see in these cases is that our specific gravity is going to decrease as our residual carbon content increases. That's logical, right? Because the specific gravity of organics is somewhere around 1. So as we come in and we look more closely here, if we zoom in and get a little bit close up on the finer scale, what we'll see, as long as we're in the coal range or the co-fired biomass at low percentages, we're going to have a reasonably linear correlation with specific gravity. What we see, though, when we look at surface area is slightly different. And so if we come in and we take a look at our residual organic content plotted here on our vertical axis versus our surface area, what we'll see is that for these biomass ashes that we have tested, we get a much larger surface area as our residual organic carbon content increases. And we'll see that if we come down here and we look at low levels, relatively low levels of residual organics, our surface area, right, is not perfectly linear, but it's not too bad either, right? Not a great R squared, but it's somewhere in the ballpark. So let's think about why this happens. Essentially, what you'll see is that when we come in and we look at grain size, going from largest openings to smallest here on the right-hand side, and then we think about our residual organic carbon content, we can see here in these cases that at the biggest particle sizes, we have these very large carbon grains. And those carbon grains have very large interscale porosity, internal porosity here, which is going to be available, that surface area is going to be available for uptake of contaminants and a variety of other sorbents. As we move into our finer grain particles here, though, we're moving to our small centispheres, and so we'll see a decrease in our specific surface area. Okay, so this is intuitively backwards for us from what we expect, right? We expect clay particles to have higher surface area, but due to this internal porosity on the carbon particles, we see the highest surface area here in the biggest particles. In addition to that, we'll see that when we start to look at some of the engineering properties of these ashes, like stiffness, for example, we're looking at small strain stiffness. As we increase our total organic carbon contents, we start here at about 1% and we increase it to 10% roughly, you can see that we'll have a decrease in our stiffness. These particles are very brittle, and so that makes sense, right? As we increase the number of those particles that are present, or the mass percentage, we'll see changes in these engineering properties. Ultimately, at the end of the day, though, we want to use these materials beneficially. As I mentioned before, the organic carbon is a serious problem for us in terms of concrete production due to the sorption of the surfactants of our air and training agents, right? So we know here in this case that we want to make air bubbles uniformly distributed throughout our concrete for the beneficial uses that we have there. What happens, though, is these organic phases will sorb our surfactants, and that's going to cause us a problem. So in some cases, when we've got these really high organic carbon content fly ashes, we want to come in and look at alternative uses for them. So let's think about the ponded ash, because that tends to be higher in organic carbon content than some of our other ashes that we deal with. We know that it is generally derived from coal as a fuel source, typically 100% coal. But we do know that it has variable composition. In some cases, ponded ash might be ash that was on specification, but it was produced in the winter when the construction was slow and we didn't have a use for it. Or it could be ash that was produced off specification, so its organic content was too high to use in concrete. We also know these ashes are often co-disposed with a variety of waste materials, and they have high variability in their ages. They've been weathered, they're wet, they've had microbial activity, and historically they're not very well characterized for their pozzolanic capability. So what we've done is we've come in and we've sampled ashes from 3 different disposal facilities. And we took ashes that were at the surface of the ash pond. So this is about 1.5 meters deep, and they were less than 10 years old. And then we took ashes that were up to about 18 meters deep, and they were on the order of about 30 to 40 years old. So the ashes that you see denoted with BH have been weathered in the field for quite a long time. In all of these cases, they were weathered in a subhumid tropical condition. So the temperature swings were from about -4 C to about 38 C throughout the year. In all cases, these ashes were sluiced to the ash pond for permanent disposal. And the results I'll show you here came from eastern bituminous coal. So generally, the first thing that we want to do is make sure that these ashes will fulfill our chemical requirements for beneficial use in concrete. And what you'll see here are the requirements that we have from ASTM C618. All right, so we know that relatively recently they've changed their classifications in terms of F ash and C ash, but generally the remaining properties are the same. So what we want to do is compare our ashes to what we have here. I want to circle back now to some SEM images to take a little bit deeper look at what we have in terms of aging and in situ cementation. So these are ponded fly ashes. All of these samples that you see here are the ashes which have been aged for about 10 years or less. And what you see is changes in the morphology. So we have surface texture. You can see those particularly pronounced here in the lower left-hand corner. But we also have evidence of in situ cementation. What you see at the interface of these 2 centispheres is a mineral interface that has been left behind as the meniscus between those 2 particles has dried, and the salts, or in this case, I think this was calcium sulfate, if I remember correctly, have precipitated here in the form of the meniscus. So we do have some in situ cementation, which is occurring when we have these ashes disposed in this way. In addition to that, what we're going to see is that over time, as these ashes age, they're going to change not only their morphology, but also their mineral phases. And so here on the left-hand side, we've got an SEM image of some typical ash that we've taken from the pond. And then on the right-hand side, we have the elemental map. And what you'll see is that if we look at where the calcium and the sulfur coincide on the surface of these ashes, we'll see places where calcium sulfate has precipitated and formed a new mineral phase on the ash itself. In addition to that, what you'll see is we can find the occurrence of iron on the surfaces themselves. In this case, the particle here, where we see the cenospheres inside the larger cenosphere, has a surface coating of iron, while this particle here is actually an iron sphere. So generally in most ashes that you'll deal with, you'll have quite a reasonable percentage of iron oxide present as well. In addition to that, in these ashes, which were disposed of in these open ponds, what you will see is formation of other things. We get microbiological activity, and you can see here that we have inclusions, right, which are diatoms present in the ashes that we have. These are the relatively near surface ponded ashes that we've dealt with. Very common phenomena. We also see formation of other mineral phases, and you can see here that we've got some other very fine ground particles as well too. So these, when we think about ponded ashes, these are not beautiful uniform cenospheres like we see coming fresh from a power generation plant. These are generally going to be very mixed materials that we have to deal with. So what happens for us when we've got these ponded ashes is we're changing the mineral phases and we're changing the morphology. And what we need to do is to be able to sort out what's going on in terms of the mineral phases here. So what we have done is we've used TGA analysis to come in and study the mass loss as a function of temperature in the ashes that we're dealing with. So what you see here are the TGA results, where we came in and we, first of all, we burned off the chemically bound water in the hydrated calcium sulfates and the clays that were present in these ponded ashes. We can come in then and we can do a temperature increase. And what you see here, these sharp spikes are evidence of the decomposition of portlandite into lime. And then you can see as we go further with increasing temperatures as well, that we get decomposition of our carbonates with these relatively spread peaks, and we get reduction of iron oxides at higher temperature. And then we can come in and we can combust the remaining unburned organic carbon content by switching the atmosphere to compressed air. So the beauty of this is it tells us exactly where the mass loss is coming from each of these samples. And so what you'll see is that when we look at this and we use what I'll call bulk mass loss measurements, things like loss on ignition, they're going to overestimate the carbon content in our weathered fly ashes. What we need to do, because these typically have so many hydrated mineral phases, is we need to come in and we need to study them either with a total carbon content measurement or with TGA. In all of these cases, we want to separate the combustion of carbon from other volatile mineral phases. And I'll show you here why that is. So if you look on the left-hand side here, this is our borehole sample. So these are ashes which have been aged for maybe 30 or 40 years. So they've been out in the field for a very long time. And if you look closely at that, the red bars that we have here at the bottom are showing bound water, right? So the deeper, older deposits have a very high percentage of bound water, which are present in the mass of the ash, right? When we compare that to relatively younger deposits that we see here on the right-hand side, right? So when we think about LOI of older weathered fly ash, it's a little bit misleading if we think of that as a surrogate for carbon content. So we have to be careful with that to make sure that we're not mixing hydrated mineral phases as a substitute in for carbon. At the end of the day, we want to use fly ash as a substitute for cement, right? So we know in this case here, we have to be concerned about the amorphous content. Do we have enough amorphous phase here in order to come in and actually use this as a cement replacement? And what you can see is that we've come in and we've got this characteristic amorphous silica hump. So that gave us confidence that we can come in and use these aged, weathered materials in our concrete. And so what we did is we came in and we performed strength activity tests. And here we took 13 samples of the weathered fly ash. So these are the ashes that were ponded for fairly long periods of time. And we used them as a cement replacement at 20% by weight. And when we perform these tests, what you'll see is that 9 out of the 13 weathered fly ash samples that we tested met the strength requirement as it is outlined in ASTM C618. The remaining samples that failed had very high LOI values, so they were over 6%, which violates the ASTM standard. In addition to that, we came in and we took those ash samples that failed, all right, and they still had sufficient strength, assuming that we gave them a longer curing time or that we did a little bit of beneficiation by using small amounts of metakaolin, right? And in all cases, the metakaolin that we added to these samples was less than 4%. So the beauty of this, what's really encouraging, is that when we come in and we take cement and we replace it with fly ash, we're saving a very large amount of CO2 gas emissions, as Professor Consali mentioned in his last presentation. And so that's a very big improvement for us in terms of sustainability. So when we think about this, what I've focused on today is concrete and using ponded ash in particular as a cement replacement in these cases. We have very, very large deposits of ponded fly ash in the United States, literally hundreds of millions of tons, many of which are being moved right now to lined landfills at a very, very high energy and cost-intensive investment. We've also come in and we've studied a variety of different types of applications that we can use for these different ash types. So what you'll see is the work that we've done is focused on looking at coal, which has low carbon content. In those cases, it's a very, very great and easy use in concrete. If we have high carbon content coal, we can in some cases use that in concrete, but it's also a very good product for use in something like a fired brick or construction material. The ponded ashes that we have worked with have proven that they are a fine substitute and fine to use in concrete and other construction materials. The biomass ash, which I mentioned today, is not great in concrete. So it's really not, there's not any benefit to using it in concrete. It is, however, highly sorptive. That activated carbon surface area, those numbers were very similar to what you'd see from a commercially produced activated carbon. So using that biomass ash as a sorptive agent in construction materials or also in fired bricks is a good application there as well. And so what you'll see here is that many of the off-specification ashes that we deal with do fulfill the requirements of C618 for beneficial use. We have weathered fly ashes, which we are not currently using, but they have more hydrated mineral phases than fresh fly ash. And so the LOI may not be the best measure in order to characterize their potential. We all know that dewatering ash ponds or dewatering anything, right, is a challenging, energy intensive and economically rigorous endeavor, right? But there is potential for beneficial use there. And so with that, I'd like to acknowledge the folks that we show here. These are collaborators, and we have received funding for our work from Southern Company and from Georgia Power. And with that, I thank you very much for your attention.
Thank you very much, Professor Burns. Very rich information shown in the lecture. Well, because time is very limited, we have to move to the next speaker. If you have any questions, please contact Professor Burns by emails or something else. Professor Burns, thank you very much. Thank you.
Thank you.